Okay, so last time I was talking about the the correspondence between rotations of S2, so rotations of the 2 sphere, and pairs of points on the 3 sphere, S3, the pairs of antipodal points on S3. So just going back to that last slide from last time. So rotations of S2 correspond to pairs plus minus q of quaternions. These pairs of quaternions correspond to point pairs of S3. And then these point pairs also correspond to points of RP3. And the way that they do that is RP3, well, the points of RP3 are actually lines through the origin in R4. And a line through the origin in R4 intersects the 3 sphere in antipodal points plus minus ABCD. Okay, and so following this through, going all the way through this correspondence, rotations of S2 correspond to points of RP3. Okay, and really what I'm interested in is using this as an example of when I can say that two geometric objects are the same in some sense. Okay, and so the idea here is to view this as a group and to also view this as a group. Okay, and then to say that these are the same group. Okay, now, to get into this, I would have to go a little bit too far off track, so I'm just going to do something very superficial here to talk about this. We've already defined the notion of a general mathematical group, but in the textbook, this is where he does this rather than us doing it earlier. So the idea of talking about these as the same group is the following. So if I have a mathematical group G1 and another mathematical group G2, these are groups. I want to define the concept of an isomorphism of groups. So there's a related notion of homomorphism, which is not as strong. An isomorphism is a particular type of homomorphism. What is an isomorphism? It's a one-to-one correspondence between the groups, so that ensures that as sets they have the same amount of stuff in them. That preserves the group structure, i.e. the group product. Right? So what is an isomorphism? So a map, I'll call it phi, from G1 to G2 is an isomorphism of groups, and G1 and G2 are said to be isomorphic. Okay, we'll see, I'll mention specifically what this means. So these are said to be isomorphic if phi is a one-to-one correspondence between G1 and G2. So it's one-to-one and onto. That preserves the products. What does that mean? It means that it maps products to products. So it takes a product of two elements, little g1 and little g2, that are both in big G1. I know this is confusing. So little g1 and little g2 are in big G1. If I look at this product, maybe even here, let's do it like this. So let's to make this less confusing, let me relabel this little g1 and little h sub 1. So both of those are in big G1. And phi takes their product, little g1 star h 1, to the product phi of G1 star phi of H1. Okay, and so this star in this case is the star in G1, and the star in this case is the star in G2, clearly because both of these things are in G2. Okay, now we don't have to think about this too much right now. The point is that two groups that are isomorphic have the same group structure. So G1 isomorphic to G2, that's the symbol we even use for isomorphic. So if two groups are isomorphic, they are identical as groups. And again, I'm getting myself in trouble. What's the word identical mean? It means that one of these groups is just a relabeling of the others. Okay, so essentially, if one group had 4 elements and it was the group A that I called A, B, C, D, and it had a certain product, then actually that's, if it's isomorphic to some other group that has elements 1, 2, 3, 4, well then I've just relabeled those elements in some way. Okay, in fact, you could even say that this isomorphism is the relabeling map. It's the relabeling function. Okay, so that's the idea. Now, why did I go through all that, and why did I mention that definition? Because I want to say something. So recall, and of course you're dealing with the quaternions a little bit more in your homework, which I just posted today. The quaternions are a group, right? So, or I should say H is a group, right? This is the quaternions. Okay, so the quaternions satisfy all of the requirements of a group. Part of your homework is showing a couple of those. Of course, they're an example of a non-commutative group, but that's fine. So the quaternions are a group, but also quaternions Q with absolute value 1 also form a group. Okay, and using your previous, even if you've never seen anything if you've never had like a full course in algebra, you can use kind of your previous classifying language experience in math to say, well, this is going to be a subgroup of this group. Okay. All right, and so these form a group, but the quaternions restricted to the ones that have absolute value 1. These also form a group, but we know that these are quaternions with absolute value 1. This can be identified with S3, right? These are points of S3. Okay, and so now what can I do here to use the notion of this isomorphism to say that S3 is actually itself a group? The idea is if I have 2 points on S3, so let's take 2 points on S3 and let's star them together. Okay, what is this product going to be on S3? Well, these 2 points are associated to 2 quaternions that I'll call Q1 and Q2. And so I define this product to be Q1 times Q2, the product occurring in the quaternions, the usual way that you just multiply quaternions. Right? And so in this way, S3 is a group. Now, what is so special about that? Because we constructed S3 as, it's just the 3 sphere, right? So for us, it's like a purely geometric thing, right? It is the 3 sphere. But it's pretty amazing that, well, like here, this construction that we've just done has shown that actually, like, it's an algebraic group as well, right? I could, in a roundabout way, I could actually define this in a kind of weird backwards way as this almost like purely algebraic thing, right? It's a group in this way. Okay, and so these geometric objects can be groups. Now, what's different about this is an example of a continuous group. So this is a continuous group. I mean, what's the difference between, say, S3 and some random group? Well, when you think of a group, right, typically one of the first things you might think of is like the integers. Right? The integers are kind of like one of the basic fundamental examples of a group. But the thing about the integers, right, is that there's gaps in them, right? The integers are not typically the type of space you think of when you think about doing geometry. So S3 is the three sphere, though, right? It's just a three-dimensional analog of the sphere. And so it's continuous in the sense that I have points near one another, and if I have 2 points near one another, and I multiply them together, then their product is near their product is close to the original product. So if you take 2 points that are near one another, you multiply them together, or rather, maybe I should phrase it like this. So if you take 2 points and you take 2 points near those points, right, then the products that you form between those two pairs are close to one another. Right? That's a better way of saying it. Okay. It's actually one of the only examples on Sn of this working. I think S1 and S3 are the only ones, are the only spheres for which that's the case. But there's plenty of examples of continuous groups. In the same way, right? Pairs of quaternions plus minus q with absolute value 1 form a group. So they form a group in the previous case under the usual quaternion multiplication. Okay, that is multiplication and using all those relations on those symbols. But in this way, the pairs plus minus q with absolute value of q equals 1, these things form a group with product. We have to define this on pairs now. So a pair plus minus q1 times plus minus q2. So this product is defined to be plus minus the usual product. Okay, and so it goes to a pair of products, but that's how we define this product. Okay, and these pairs are in one-to-one correspondence with the points of RP3, but these pairs are in one-to-one correspondence with points of RP3. Thus, we can move this group structure here on pairs of quaternions to RP3, thus moving the group structure. This is the notion of isomorphic groups. So the group that I would form from RP3 would be isomorphic to this one. RP3 can also be seen as a group. Okay. This one might be a little bit more surprising to you than S3 because, with S3 you might try to reason with yourself why, a multiplication on S3 would make sense. But with RP3, the way that it's defined, right, in the usual way that we define these projective spaces, it's not at all clear what a product of these things would look like. So this is a group. Okay, in the same way. All right. And so the reason I wanted you to see this is just I wanted you to see that these objects are not, it's not black and white. It's not totally cut and dry here. When you're talking about different fields of math, so if you're talking about group theory or geometry or algebra or analysis or whatever, it's not like there's some invisible wall like dividing those things. There's tons of overlap. And so, here's an example of these spaces that we encountered that were purely geometric, whatever that means to us. But actually, it turns out they have a group structure, right? And so they could be studied from the angle of group theory. Okay, and that's kind of a recurring theme in math in general, is that there's often many ways in which you can actually approach some object is not, does not merely belong to like a single narrow domain. Okay, so the last thing I wanted to say before finally moving on to the very last chapter is we began, of course, studying Euclidean geometry. From Euclidean geometry, we went on to, after moving through the linear algebra that we introduced, right, and the vector algebra that we introduced, we went into projective geometry. Now, we didn't mention it at the time, but I've mentioned it since then, that vector algebra stuff that we did is actually an intermediate type of geometry before we impose the Euclideanness on it. It's an intermediate type of geometry known as affine geometry. So we went Euclidean, and then we went from Euclidean geometry to affine geometry, but we didn't say it at the time. And then we went from there to projective geometry. Now, I've drawn this line before, and I've said that, here you have the most restrictive, and then you're getting less and less restrictive as you go on. So in Euclidean geometry, you're well aware of all the restrictions that are imposed on it. Affine geometry, what is the stuff that matters? Well, maybe before I talk about affine. Projective geometry, we know that a lot of notions are tossed out, right? We can't talk about notions of distance, right? In fact, the main notions that we can talk about is straightness of lines, right? Collinearity, that stuff. So with affine geometry, it's like projective geometry, except I have an extra notion of parallelism. So an example of that, what I said previously was that affine geometry is typically described as it's like you forgot where the origin was. There's no specialness of the origin. Okay, there's no special point. If you're thinking about it as viewing an image, you're viewing the image from a projection at infinity. So an example of this is in artwork coming from East Asia. So this is a Japanese painting from the 1700s. So this is not projective, but it's not Euclidean in another sense, right? Look at what's going on here. We have tiles here, both on this, both on the walkway that she's standing on and behind her. These tiles, and we know that like they're all equal, they're all drawn of equal size, but like we know that as they get further away from our view, whatever our view is, they should look smaller, even if they're not, but they don't here. All right, so this is a very strange viewpoint because it's flat, right? It has flatness, but it doesn't have flatness like something that didn't preserve these parallel lines. Okay, so it doesn't have flatness in the same way that a lot of the European drawings prior to the Renaissance did. So what is it that I'm looking at? This is like a projection from infinity, or think about it as a photograph viewed from very far off with infinite zoom. Okay, that's basically what I'm looking at here. Okay, there's another example of an affine type of geometry, which is called axonometric projection, as an example of an affine map. So for instance, say you want to depict an object in 3 dimensions, but you want the correct proportions in some given direction. So there is an example. You saw images like this. The point is that this is just like affine geometry is kind of like a compromise between the rigidness of Euclidean geometry and the complete floppiness of projective geometry. Affine geometry, or an affine view, is like it's a compromise between like the realism, like the realistic drawing, and one that's totally unrealistic but maybe looks good. Okay. Anyway, so that was kind of the last thing that I wanted to tidy up there. Okay. So finally we are at our, main goal of our course, which is the discussion of non-Euclidean geometry. Now, you might protest and say, as I mentioned earlier, that we've actually already seen examples of non-Euclidean geometry. Okay, so we saw an example. So we saw the example of spherical geometry. Okay. But I explained why the ancients didn't view, or even why, a lot of mathematicians, all the way up to the mid-1800s, didn't view spherical geometry as non-Euclidean in a sense. And the main reason was that they didn't have a lot of the mathematical tools to understand that it wasn't Euclidean just because it sat in Euclidean space. You could very much define it in a way that that showed directly this is non-Euclidean, and it's really not, just because it can sit inside this Euclidean space doesn't really mean anything. Doesn't make it less non-Euclidean. But the main thing about spherical geometry, something else that I haven't mentioned yet, is that spherical geometry fails the parallel postulate. But it also fails others. In fact, it fails 3 out of 5 Euclidean postulates, but it also fails 2 other postulates of Euclid's postulates. So I mentioned earlier that it did fail another one, right? So it fails the parallel postulate. That's the 5th postulate. It fails 1, but it fails 2 others, right? So in total, it only satisfies 2 out of 5 of Euclid's postulates. Okay, let's see which ones those are. Okay, so let's go back to our handy list of Euclidean postulates from way back. So, where is our list? I'm pretty sure it's listed nicely in this textbook somewhere. I'm in chapter 1 now. Well, it's looking, let's see here. Well, I am now, could have sworn we had a list of these things. Well, maybe not. Maybe there's not a nice, convenient list of these Euclidean postulates. Okay, well, anyway, so I won't list out the Euclidean postulates then. So then what I'll say is, which of the 2 other ones does it fail? So the parallel postulate, you're familiar with that. There's also the postulate that between any 2 points, there's a unique line, right? So antipodal points fail the uniqueness of lines. Right? So if you choose antipodal points on your sphere, and you look at the, quote, lines between them, there's not just one, there's infinitely many, right? So this definitely fails that postulate. The other postulate that it fails off the top of my head is the one that says that the plane contains circles of arbitrary radius, so or lines of arbitrary length, right? And while, yes, like great circles can be extended indefinitely, in a sense, they do not have arbitrary, they don't have arbitrary length, so that is failed as well. But you don't have to worry about that. The main thing to worry about is it fails parallel postulate. That's good. That's what we want for it to be non-Euclidean. But it also fails uniqueness of lines, right? Which somehow makes it, it makes it useless for one of the original purposes, right? So recall, kind of the thing that set mathematicians on this path to begin with, the main pursuit was to either prove the parallel postulate, assuming the others, or to show that there exists a geometry which satisfies all of the postulates except the parallel postulates. Except the parallel postulate. Okay. And so, I can't use spherical geometry for either of these things because spherical geometry, it doesn't satisfy other postulates. And so any question about using those other, saying that the parallel postulate follows from one of the others, it's like, well, maybe it doesn't follow from the remaining postulates that spherical geometry satisfies, but what if adding in two of these other postulates gives you the parallel postulate, right? So spherical geometry can't be used as this example. So of course it's going to be shown by us that proving the parallel postulate is not going to be possible, and so what occurs is that there does in fact exist a geometry which satisfies all of the postulates except the parallel postulate. What's important to note, maybe is satisfying from our perspective, is that this construction is not pathological in the sense that it's not like a lot of effort had to go into constructing this specifically to fail the parallel postulate. This construction is actually a very natural thing that would come from something we've already seen. Okay. All right. In fact, it arises from RP1. Okay. So this non-Euclidean geometry we construct arises from RP1, the real projective line. Okay. In particular, it arises from our attempt to extend RP1 to be a plane. Okay. Okay, and so our goal for the next few lectures is to extend the projective line to a plane. And I'm going to give an overview of this today and on Friday before getting into the specifics of where these things come from and why the pictures look the way they do. Okay. So, extending the projective line to a plane. How does this work? The idea is when I had RP1, right? What were the quantities associated with RP1 that were important? Well, RP1 is a projective line, and as such, being this one-dimensional thing, it doesn't have a lot of room, right? When you're looking at a one-dimensional object, it's very hard to see what's going on because there's just not much room. Okay. And so what we need to do here is give ourselves a little bit more space so that we can actually see geometrically what's happening. And that's kind of the intuition behind wanting to extend RP1 to be a plane. And so what is the way that we would do this? Well, we want to view RP1 as the boundary at infinity, or the line at infinity for some plane. Okay. So we want to view RP1 as the boundary at infinity for our plane. Okay. That we're constructing. Okay, and I'll draw pictures of how we're going to do this. But when you talk about RP1, we have some fundamental things. So using our Klein approach, the most important thing for us to consider is the group of transformations. Well, we've already worked out what the group of transformations for RP1 is. These are the fractional linear transformations, right? So our transformations look like this: ax plus b over cx plus d, where a, b, c, and d are real numbers, and we want ad minus bc to be non-zero, right? Right? Viewing them as behaving like matrices, of course, this guarantees that these transformations are invertible, right? And so to make them an actual group of transformations, that's what's needed. And so these fractional linear transformations were our isometry group for RP1. But also, of course, we could consider what quantities were preserved by this, and cross ratios. Right? The cross ratio was preserved. So cross ratio was the thing preserved, and these were our transformations. Okay. Now, how is this going to give me the transformation group for my RP1 extended to a plane? First of all, how am I going to do this? So what is the fundamental idea? And maybe I need to give myself a little bit more space here. So what's the fundamental idea? Fundamental idea is I have a line. So RP1 is a line, right, geometrically. Okay. Now in your head, you can think about whatever sort of interpretation RP1 you want to think about. You could think about it as, the circle realizes some line, but there's some point at infinity for our real projective line. But RP1, if I wanted to draw it, looks like this. How am I going to extend this to a plane? Well, I already have the usual plane. Why don't I view my normal plane, that is having x and y axes, as containing RP1 as the x-axis? Okay. Well, this doesn't quite fit the description I was going with, right? So I want to view RP1 as the boundary at infinity for our plane. So this thing has to be a boundary at infinity. It's not actually included in the plane. And so the idea is to include it as a dashed line. That is, it's not actually included in the plane. So there's my copy of RP1, and then I have an upper plane and a lower plane. Of course, these are half planes, right? Now, they're half in the sense of, this is how I'm drawing them, right? So this is the upper half plane and the lower half plane. Okay. And so, looking at this, RP1 is certainly a boundary for these, but I want to pick one. Why? I want to pick one because when it comes to defining the transformations that I'm going to talk about, I don't want them to mix the half planes. So I don't want a transformation to send a point in the upper half plane to the lower half plane, and vice versa. Now, why wouldn't I want that geometrically? Well, geometrically, this boundary in this way is something that can't be crossed, right? And so points that would end up, mixed between would be points that could not be gotten to, right? Like, so you take a point and another point, that's a line segment. You map it to 2 points. Maybe only one of those points is in the one's in the upper half plane, one's in the lower half plane. The problem with that geometrically, of course, is that points in the upper and lower half plane are totally separated. There's no way to connect those. So you would end up doing stuff like mapping line segments to things that aren't line segments, right? Because they couldn't even be completed. So geometrically, that's why you would pick one. Now, does it matter which one you pick? You can develop exactly everything that we developed picking either one. We're going to pick the upper half plane. Okay, so we are going to look at the upper half plane. And so what we look at is this. So our picture, our model space for the geometry that we're going to come up with is the upper half plane. That is, it extends infinitely in the positive y direction. This x-axis is not included. It is a boundary, right? It is open here. Okay, and that's what I'm identifying as my copy of RP1, that line sitting at the boundary. So this is the model that I'm going to use, okay, for all of these things. And the main thing is we want our transformations to map upper half plane to upper half plane. Now, if we were going to use the lower half plane, we want the same statement true for the lower half plane. The idea is we want these transformations to leave whether it's an upper or lower half plane fixed. Okay? And so this is going to be a major thing that informs us how we're going to try to define this. Okay, so going back, what's the idea? Well, the idea is if I want to extend my transformations to be defined on a line, right? So here my x is a real number, right? Viewed in this picture, if I were mapping an x, it would be some point here on the boundary, right? So a point here on my boundary gets mapped, that's just represented by a real number, that gets mapped somewhere by this linear fractional transformation. But the idea is I want to know how a point here, right, gets mapped by some kind of linear transformation-like thing. I want to use these linear fractional transformations to describe or to define transformations on the upper half plane instead of just a one-dimensional line. The idea then is to replace x with z, right? So to replace x, which is a real number, with z, which is a complex number, which algebraically we could think of as an ordered pair of real numbers, of course. So we identify this point here with a point z. It's a complex number, right? A plus ib. Okay, so that is the idea. And now if I do that, then what I get is a transformation that looks like this. F of z is a z plus b over cz plus d, right? Okay. Now, what's the issue with this? All right, so what is the problem with this? So the problem is that, so what is the issue with this? So here's my question. I'm not going to write the answer. I'm just going to say what the problem is. The problem is that if I just swap out x for a complex variable z here, the issue becomes exactly what I was talking about before, because, oh, did I accidentally? There we go. There we go. Because basically, this upper half plane these half planes get divided by this boundary line. And so if I want to see how to extend these things, I can't just straightforwardly, reproduce these transformations by swapping to a complex variable, because it could mix the half planes. It could map upper to lower, and it's not always clear what should extend to what. So an example. So here's an example to consider. In linear fractional transformations, I would have the example that sends x to minus x. So what should this extend to? So what should this extend to? Now you might say, should it extend to z mapping to minus z? So let you think about that for like 5 seconds. So should this extend to z mapping to minus z? Okay, well, this maps the upper half plane to the lower. All right, z getting sent to minus z takes upper to lower, so that's no good. Right? And so immediately, it's not always obvious how we should extend these. How to extend a linear fractional transformation ax plus b over cx plus d to the version where I've swapped with complex variables. Okay, it's just not always obvious how to extend in this way. But nevertheless, we can tweak this to work exactly as we want. And that's exactly what we're going to do in the next sections. Okay, so we'll do this precisely a bit later. Okay. All right. Okay. So, right now it's not clear exactly how this process works, but take it, on faith for a second that this does actually work. Okay. So, this works to extend our transformations of RP1 into transformations of our upper half plane defined in this way. So then the big question is, what does the geometry of this upper half plane look like? Well, it doesn't look like a weird Euclidean geometry of the upper half plane, because the transformation group we get comes from this extension from RP1 into this transformation group that involves these transformations that are like transformations for RP1 extended to a complex variable. So you might already know what these are. These are the Merbius transformations. Okay. So these are the Merbius transformations. And anyway, and so the question is, what does the geometry of the upper half plane with Merbius transformations look like? The reason why this is saved till the very end of the course is that we just now in chapter 7 and 8 have been talking about how transformation group gives geometry, right? So group of transformations gives rise to geometry, rather than going in the other direction, which is what was done, for most of history. And so our group of transformations, these extended RP1 transformations, are going to give rise to a geometry. And the question is, what does the geometry look like? Well, here's my boundary. Here's my boundary RP1. What do lines look like? So here's a point, say P. Here's a point Q. What is the line between P and Q? Well, it's the vertical line between P and Q. And so my line here is exactly the vertical line connecting P and Q. Okay, that's cool. But what about points that might look something like this, right? That are not vertical from one another. So what about 2 points like that? Well, it turns out that for points like this, the unique line associated to them is a semicircle. Now, I know that that's not actually a semicircle, but bear with me. It's a semicircle with its center on this x-axis that's missing, right? This boundary RP1. And so here's a line. I'll call this line L1. Here's another line, L2, between some 2 points. Lines are uniquely determined. They satisfy that postulate. These are examples of parallel lines. So L1 is parallel to L2. Okay. What else? Well, you can already see from this that if my lines are either semicircles centered on the x-axis of some radius or these vertical lines, well, the question is, if I formulate the parallel postulate in terms of Playfair's axiom, boom, there's a point not on one of these lines. How many parallel lines through that point exist that are parallel, or so how many lines through that point exist that are parallel to one of these other lines? Infinitely many, right? I could draw a vertical line through that point. I could draw any one of these semicircles that passes through that point. So fails the parallel postulate. Okay, but it satisfies all other postulates. So satisfies all Euclidean postulates except the parallel postulate. Okay. Another thing that is totally different from the other sorts of, especially if you're thinking about projective geometry, the fact that this gets extended from RP1, where distance was not a thing, but gets extended to a thing that has distance. So note, we also have a notion of distance. We'll talk about this later. Why is this so shocking? Well, there was no distance in RP1. Right? Sensibly talking about distance in RP1 didn't make any sense because RP1 was defined, as this projective geometry thing where you can't talk about distance, right? So definitely don't have a notion of distance or length in RP1, but we are going to have a notion of distance here. It's going to be a non-Euclidean distance. Okay. In fact, I will draw later some of the weird stuff that happens. One of them is, say that I have a thing drawn here. Note, this is not a line in this space. So it's an object, it's a geometric object, but it's not a line in this space. This and this may have the same length. So as you get closer to the upper half plane, or to the boundary of the upper half plane, distant or lengths that appear smaller are actually much longer than they would appear. So if you think about this, it's like much, much less near the boundary is worth much, much more up here away from the boundary. So I'll draw some pictures of that before we finish this course showing exactly that. So this is the overview. I did nothing showing that this is the geometry you get. Okay, and so what we're going to spend the remainder of the time in the class doing is showing why the transformations that we get give us this geometry. Okay, so we'll do that starting next time. So I'll start here next time. So I'll see you all on Friday. Have a look at the homework that I posted earlier.